Okay. This, I just want to, we did a problem like this, right? This is, we did the one with the hunter and the camp. Remember that? Okay, this would be, we're not gonna do this one, but this would be a slightly harder question. If you, we can just talk just for a second about how maybe we can set this up. So let's say that you've got a guy who is 2 miles from the nearest point on a coastline, and he has to get 3 miles down the coast and 1 mile inland. And he's in a boat, and he can travel in the boat at 2 miles per hour, and he can walk at 4 miles per hour. And so you'd want to figure out where does he aim to minimize his time, right? We could do this, right? No, we don't have to do it, but I mean, we just, I want to, let's at least just talk about how we could set this up. So what would, I mean, this, we did one similar to this, but this has broader applications than you might think. So they've already given us X is how far down the coast he's gonna aim, right? So just, we don't have to get specific, but how would we set this up? We're trying to minimize what? Time. And time, we said, is related to speed and distance. How? Speed equals distance over time. So time equals d divided by v. Good. Okay. And we could figure out, we know what the v's are, right? For part 1, the v is 2, and for part 2, it's 4 in this case, right? For this problem. And so really the distances are the only things that would depend on our variable, right? And we would just say if this is x, and that's 2, then what's the distance in the water? So if we're saying that this distance where we're aiming, how far we're aiming down the coast, we're calling that x.
Square root of x squared.
Right, by Pythagorean theorem, okay? And then down here, the distance across the land would be square root of
3 minus x squared.
plus 1 squared, plus 1, right? Okay, and we could figure this out, right? Our domain would be from where to where? X would be from, he's not gonna go backwards,
0 to
obviously.
3.
So 0 to 3, and we could do this, that's not a big deal. Right? We can do that, we just do the calculus. That seems like kind of a contrived problem, but what's something, when I saw this kind of struck a chord. This is pretty cool. We could, instead of making this a boat and a coastline and water and land, we could draw the same picture where this is, say, a laser, and these are 2 different media. One of them's glass and one of them's vacuum, or one of them's glass and one of them's water, or something like that. And light is refracted when it gets bent, right? Like for example, we'll talk about this in physics here later on in the year. Like if you look in a pool, like let's say you're hunting for you're gonna try to spear a fish or something. If you see the fish in the water, do you aim right at the fish?
No.
Where would you aim?
It's right now. About it.
You'd aim below it a little bit, right? Because it looks like things always appear to be a little shallower than they are because the light's bent, right? So it seems like the light is coming from, from a shallower angle than it actually is. Does that make sense? Or actually, in this case, it would look like it's coming from deeper, but this is the opposite of what would happen with water. Okay, does that make sense? Anyway, so there's this refractive effect when light passes between 2 boundaries. What causes that? Well, actually, what causes it is that the speed of light is a little bit different in the 2 different media. It's going to travel faster in a vacuum than it travels in water, for example, okay? And so how do you figure out what the path that light's going to take is? Well, you can use Snell's law. You can use just the angle of incidence is related to the angle of refraction by the ratio of the indices of refraction. And so you can use a formula, but here's a really cool way you can do it. And you can actually define a lot of the properties of light by just making the simple assumption that light's going to get from point A to point B in the fastest possible time. It always works that way. It's called Huygens principle, and it's like an archaic thing that you would never do, but you can. You can do a lot of optics just with that one simple assumption, and so you could do this problem the exact same way you did it up here if you just made a few substitutions. If you just said, okay, the distances are geometric, those would stay the same, let's say, but instead of 2 miles per hour and 4 miles per hour, you could just instead talk about the speed of light in medium A and medium B, and you get the path that light chooses to follow. It's going to minimize transit time. The math gods somehow figure that out, and that's the path that light takes, right? So you can actually, this applies to lots of other things other than just a rowboat trying to get from point A to point B in the fastest time, right? Okay, this is kind of, well, we're talking about physics. I think this is a pretty cool problem. I've somehow always overlooked this one. Maybe this isn't in the paper book, I don't know. But it's in the online book. This is kind of cool. So this has to do with some of the things that we've been talking about in physics, right? This has to do with, you know, what's the tensile strength. And we've talked about, shear forces, and we haven't gotten into really like braking strength and things like that, but it's strongly related. So what about something like this? If we've got this log with a 20-inch diameter, and we want to cut a square timber out of it for a beam, what are the dimensions of the beam that's going to be the strongest beam? Okay? And there's really just two things we need to know. The strength of the beam is directly proportional to the width. So you double the width, you double the strength, but it's proportional to the square of the height, right? And you notice that when you look at things like I-beams on girders and buildings, or if you look at floor trusses, they're always pretty long this way, right? They're pretty deep, but not very wide, because the height is a more critical dimension than the width when you're figuring the strength of a beam. So what could we do? What if we wanted to make the strongest beam out of this log? How would we cut it? But it's got to be a rectangular profile so it fits nicely with the other materials. What do we think? We've got our variables, I guess, are W and H instead of X and Y. Oh well. How do we write down our primary equation then? Strength S.
equals
It's proportional to what?
W
Say it again.
or H squared.
WH squared. Everybody agree? So then if we want to write that as an equation, what's it look like?
KW.
There you go, some constant, which we don't know, but some constant of proportionality times W times H squared. Okay? All right, so we want to maximize strength. What's our constraint in this case? The 20. Okay, so how does that relate W and H? Okay, so W squared plus H squared equals 20 squared? What substitution would we make?
Solve for H squared.
H squared, yeah, there you go. There's an H squared. There's an H squared, right? So we could say H squared equals 400 minus W squared. Right, make that substitution, and look what we get. So then we get S equals KW times that. Right? And I could go ahead and distribute the W, and I just get a polynomial, which is great. So S of W equals K times 400W minus W cubed. And what's going to be our domain in this case? 0 to 20, yeah. That makes sense? Okay, something like that. Guess there's no reason we couldn't pick 0 and 20. I mean, it's obviously 0 and 20 aren't going to work, but those are the limits at least of our domain. Okay? And so this is a pretty easy one, right? It's just a polynomial. What's our derivative going to be? Okay, so S prime equals 0 when what? 3W squared equals 400? So W equals the square root 400 thirds. And then second derivative, what are we going to get? Negative, that's going to go away, right? So negative 6kW. But what's the important thing there? What's going to be for our domain includes just positive values. So it's going to be negative everywhere, right? Good. So then that's going to give us the maximum that we want, isn't it? Right? So, I mean, we can make our table, but we can see what the outcome's going to be. This is going to be the value of W that's going to give us our maximum strength. So if that's W, what does that make H? So H squared would be, well, if I write W squared is going to be 400 thirds. So we're going to get 2/3 of 4, so 800 thirds. H squared equals that. So H would equal, what's that going to be? 20, is that right? 20 times the square root of 2, yeah, over square root of 3. Right? So we could rationalize that if we want to. We'd probably just make it a decimal. Right? So that's going to give us, so what are those roughly? Just as decimals. I'm just kind of curious what we get for answers here.
W is 11.54, and for H I got 16.3.
Say it again, 15.33.
16.33.
So that gives you an idea about the dimensions of that then, right? How you want to cut that mean. Okay? That's, honestly, that's kind of cool to be able to do. I mean, it's like if you were building a shop or something. My parents, they live out in Eastern Oregon. I mean, I think of Eastern Oregon being way over there. They live in Lostine. And they field their own lumber lots of times where they'll have, you know, if trees get blown over or something, they'll bring in a guy with a portable mill and they'll just cut all their own, just, you know, raw dimension lumber and dry it. And you can use it for building materials, but you gotta know how you're gonna cut your beams. You know, if you wanna minimize the weight, maximize the strength, how would you take a raw piece of timber and cut it into a beam? Well, we just figured it out. That's it, right? Okay, so I'm prepared to let you work a little bit. I got a question for you. So on the test, I would like to do, I want to do at least one part of it where I want to see you actually do the optimization. I want to see you go through and organize. I'm concerned that, I mean, a good thing, there's a lot of good that comes with getting feedback, you know, doing work where you can know if you get it right or wrong immediately. And so I fiercely defend the idea that you should use computer adaptive stuff a lot in math. But I also want to make sure that you're developing the ability to organize what you're doing, because that is really important in math. And so I'd like to do a part of the test where you actually have to, I'll give you a paper and pencil problem or two for optimization. So do you need, I don't think I need to do this, but do you need some extra problems out of the book to work on that? Or are you okay just kind of going through that process, paper and pencil process, while you're doing the stuff online? Okay, but just be aware that I want to see, you know, I mean, there are some pretty distinctive steps. Does everyone need another copy of that handout I gave you on the recipe for optimization? It's on the Calculus Moodle site too, but I can print one out for you if you need it. But I want to see that. I want to see the process organized where it's easy to see. I mean, and what I'm looking at on this is not really what the answer is. I want to see that you can, you know, you can stitch together those steps in a way that makes sense. Because in college, that's going to be important. You know, that's a lot of it is, I can remember taking tests in college where if whoever was grading it, the TA that was grading it, if he couldn't see what was going on in 15 seconds, he just marked it wrong, right? I mean, because you know, that's kind of the way it is. You just got to make it, you got to be able to communicate your mathematical thinking in a way that's clear, right? Does that make sense? Okay. All right. You can work and get questions answered.
whole like player on there. He's like singling out a player. And Jerome said he really wants to like let it go because he thinks it's funny. And he was like trying to apologize. He was like, "Now what do you want us to do? Because I feel bad. Because like I really want to do this." And I was like, "What if you just have us tape over the sleigh ramp before the 100 foot? Because they might also get the message. And then if they see that there's tape there, then that might be funny too." Yeah, censored, exactly.
The thing is that they also want still to know what to say.
Yeah,
Are
exactly.
they doing the donation thing still?
So that was the Zog thing, and I still have like $8 in my car. I had to spend 20 and 100 on like another shirt or another 2 shirts kind of thing. But I'm gonna do that tonight before the game. I'm just gonna text Adrian. Use that text as well.
Oh.
Yeah, I'm just gonna do it myself because they can't do it through the school according to the office.
They can't like announce it?